Welcome to the next lecture, and if you recall, we were discussing about types of induction motor. We know there are two types of three-phase induction motors. One is called slip ring or wound rotor type induction motor, and the other is called cage, squirrel cage type induction motor. In fact, we are discussing cage type induction motor. In cage type induction motor, what happens is this: it is in the construction of the rotor which is different from that of the three phase slip ring type induction motor. In the cage rotor, as you know, I will quickly tell, there are enough rotor bars, large number of rotor bars will be there, and they will be like this. In these slots, this is iron and it will be embedded with these bars, rotor bars they call it. And on the other side also they will be terminated here. For each one of them they will find an end, but all these terminals are short circuited at both the ends by what is known as end rings. This side and also this side, all are short circuited. Therefore, in the cage type induction motor, no rotor terminals available. Cage motors, no rotor terminals, so that you will not be able to connect any external resistance to improve starting torque, etc. No slip ring, no brass like that. Therefore, this is how physically looking at a given induction motor, you can easily see if you at the end cover, if you remove, you will find in cage type induction motors there are 3 slip rings and 3 brushes, but in cage type induction motor nothing available, only rotor, and at both ends it is shorted. I was telling about how to then deal with this, and such a cage induction motor will be represented in this way. Stator winding is of course our traditional 3-phase distributed winding, and cage rotor is shown like this symbolically, and they are shorted, that is all, no rotor terminals. Now, what happens is this, as an observation I was telling you, if you supply the stator coils, you will find rotor is started rotating. Now, the question is how it starts moving. The answer is not difficult to obtain, because of the fact that in normal slip ring induction motor, you have to keep the rotor terminals shorted. Here also rotor terminals are kept shorted. So, to understand, I told you like this, you think in this way that these are the cage bar. You first imagine that one end ring is removed, that is these are the bars here like this. You consider this bar is removed first. Therefore, it is like a open circuit induction motor, and in each conductor there will be induced voltage. Although with one end ring open, the things cannot move because there is no rotor current and hence no rotor poles. The important point is rotor should produce same number of poles as that of the stator, no matter what kind of winding you use. For example, you could have a 3-phase induction motor whose stator is wound for 3-phase on the stator, rotor is wound for 2-phase with 2 slip rings, etc. and things will run, provided these 2 windings are wound for the same number of poles. That is the most crucial point, because stator does not know what kind of polyphase winding rotor is having. It is only interested to know whether it is developing same number of poles or not. Based on that, stator draws extra current from the supply when rotor current flows. So, I told you last time, very quickly I am telling that these bars can be shown to have a polyphase balanced polyphase winding, and when the other end rings, now you imagine other end ring is also put, so that all terminals are shorted here. Therefore, this cage induction motor, it was shown to be of number of phases can be thought of 2s by p, a balanced polyphase winding, and therefore, it too will produce same number of poles. So, that is the idea. Therefore, in cage induction motor, the advantage is the construction of rotor is very simple, no maintenance because no slip ring bars, etc., and cost of this machine will be higher compared to a slip ring induction motor, because there are no copper slip rings, neither brushes. Maintenance problem will be also least so far as the rotor is concerned. However, it suffers a disadvantage if you say that the starting torque cannot be improved by inserting some external resistance as we were doing in case of slip ring induction motor. Nonetheless, this cage induction motor has got another interesting property, that is the thing that if your rotor, interesting property, let me write, those are obvious, interesting property. Of cage induction motor, cage type induction motor. What is that interesting property? It is like this. Suppose you have a fixed rotor, okay, with all bars, number of bars are there, okay, and these are shorted. This is how I show a cage induction motor. This is the rotor. On the stator, I have got a 3-phase winding, and it produces p pole, 3-phase winding wound for p poles. Now, what I will do is this, I will have the same rotor, but suppose the stator winding I change, balanced 3-phase winding nonetheless, and it is suppose number of poles is suppose 2p. Suppose it is 2 pole, it is 4 pole stator windings. Rotor, same rotor I will not change, same rotor. Stator is changed, stator change means stator winding is changed, one for p pole, another for 2 p poles. And once again you energize this machine and this machine, in both the cases the machine will rotate. In other words, what I am telling, and this is not going to happen if it is a slip ring induction motor. For slip ring induction motor, we know both stator and rotor is to be wound for same number of poles, and then you short circuit it, is not? This is stator, this is rotor. But for this machine, if you do not do anything with the rotor, keep it as p pole and stator winding, rewind it for 2 p poles, energize the supply, and machine is obviously not going to start, not going to run, simply because the number of poles are different. produced by stator and rotor. But the interesting point is, if it is a cage induction motor, stator winding you change to in general any number of poles, still it will work. Now, the question is why it should. The answer to this is not very far to seek, that I will tell right now, but this is another interesting advantage of a cage induction motor. In fact, as I told you, an induction motor is maybe considered to be roughly a constant speed motor like DC shunt motor, because variation of speed from no load to full load is only very little, is not. If it is a 4-pole machine, synchronous speed is 1500 rpm, therefore, variation of speed will be little. From no load it will be close to 1500, then full load may be 1430 rpm. Therefore, change in variation of speed is only 70 rpm. As a percentage you can calculate, very little change, maybe 2 to 5% of the synchronous speed, that change will occur. So, in general it is considered to be rather a constant speed induction motor. In fact, in earlier days, few decades back also it was considered like that. So, to control the speed of the induction motor, one method suggested, see, we have discussed many a times that the rotor will settle down to a speed very close to synchronous speed under no load condition and slightly below synchronous speed even when it is fully loaded. Therefore, it is the synchronous speed which is going to decide about the speed at which induction motor is going to run. For example, if it is a 6-pole induction motor, 50 hertz is the supply, I will tell okay, machine will run below 1000 rpm and close to 1000 rpm without much workout. I mean, I am sure it may be 950 rpm, 940 rpm like that. If it is 8-pole machine, similarly for 8-pole I can calculate synchronous speed, and I am sure machine is going to run whatever is that speed, synchronous speed, close to that, but below that. Now, synchronous speed Ns is equal to 120 f by p, so much rpm. We know that. Earlier days, in order to, therefore, supply frequency is fixed, machine number of poles are fixed. Therefore, it looks like you cannot control synchronous speed. The indication was that from this equation, I note that if by any chance, by hook or by crook, if I could change the value of synchronous speed, then I would expect the rotor speed to vary also accordingly, so that this term that it is a constant speed induction motor could be removed. So, one way was that okay, you on the stator you use 2 stator windings, 2 separate stator windings. Suppose one is wound for 2 poles and another is wound for 4 poles. 2 completely separate 3-phase distributed winding in the stator slots you accommodate, and at a time I will either energize that 2-pole winding or the 4-pole winding, and my rotor will be a cage induction motor. Therefore, when the 2-pole stator winding is energized, the synchronous speed is going to be 3000 rpm, and therefore, I would expect the motor speed will be close to 3000 rpm, maybe 2950 rpm or so, but close to that. And if I want to run at 1500 rpm, therefore, I will de-energize the windings corresponding to 2 pole and energize the 3 phase winding on the stator, which is wound for 4 pole. Supply frequency is fixed, then the synchronous speed will be 1500 rpm, and I would expect machine will run close to 1500 rpm. Therefore, we can say okay, this induction motor having 2 stator windings, 2 separate stator windings, one will be energized at a time, can give you at best 2 level of speed. One is close to 3000 rpm, another is close to 1500 rpm. And that is possible provided the rotor is cage. That is what I am trying to tell. So, cage induction motor also became popular because of this. People say the cage rotor, I will write that statement, cage rotor can adjust to varying number of stator poles on its own. You do not have to change the rotor. Okay. Now, the question is why it is like this. It is because of the fact, if you draw the developed diagram of the cage bar, it will be like this. Let me draw a few at least. Like this. Top view, you have developed it and looking from the top. I am sorry, it is quite big. Like this it goes. Where are the bars? These two are end rings. Also this one. And these are the bars, copper bars, which are short circuited at both the ends, and it continues like this. Now, suppose number of stator poles is 2 pole or 4 pole, whatever it is. Suppose this conductor is under the center of the north pole. Then under the center of the south pole, there will be a bar present, and that is all, because after all north and south pole dictated by stator decides the induced voltage and current in the rotor bars, because rotor bars induced voltage of this bar will be BLV, and that BLV in whichever way it has been decided by the stator coils will have that polarity of the voltage, etc. And there you will find another bar which is 180 degree electrical apart after the south pole, another bar exists. No matter whether the stator is 4 pole or 2 pole or 6 pole, wherever a bar is there, you can find out after a distance of 180 degree electrical apart decided by the stator poles, a bar is present, and you can consider this to be a turn, and current will flow like this. Therefore, it will produce as many poles as produced by the stator coils. That is the beauty, it is already shorted, but in slip ring induction motor, no, that is not possible, because the return conductor of a particular turn is already decided by me, and I have taken all the care that if one coil side is under the center of the north pole, generally other coil side will be under the center of the south pole, and they have got their own identity, a separate coil. But here, because of the fact that all the coil ends are shorted, no one knows whether this fellow will act as return conductor of this fellow or not. It will be decided solely by the stator number of poles. If this is under the center of the north pole, you will find a bar exists where this bar will be under the center of the south pole. Both of them will have same induced voltage, additive voltage, and current will return like this. Now, what I am trying to tell, if the same, I will now draw just like this. This is N bar, N ring, and these are your bars, number of bars are present like this. If somebody says he is accommodating more poles created by stator, winding you have changed on the stator. If suppose this fellow is under north pole, the next peak of the south pole is suppose here. Once again north south. Here this conductor will feel, oh, my return conductor is here, I should circulate current like this. That is why people say a cage induction motor can adjust itself to any number of poles, I mean in general any number of poles as produced by the stator. So, it is a very nice thing. In fact, this was one of the reasons that cage induction motor you can have at least 2 speeds, provided you have got 2 state of stator windings. I will to have a complete type of statement on this ground, I told you, you have 2 separate stator windings, okay? But it is possible, which I indicated while discussing about my winding layouts etc., that it is also possible sometimes, not it is also possible that you use same winding which is wound for say 4 poles and reconnect the winding groups such that it will produce 2 pole. That is what I am telling new thing now. You can have 2 separate stator 3-phase coils, energize one at a time. Obviously, the utilization of the machine space available for copper you are reducing. Can it be possible I will use a single 3-phase winding distributed, but by reconnecting the groups in a particular fashion, is it possible to get a 3-phase winding which will sometimes behave like a 2-pole. I change the interconnection of those coils and it will be behaving now like a 4-pole. Yes, it is possible. For example, suppose only R phase I am showing simplest thing. Suppose you have 4 slots, I mean stator I should draw. So, it will be like this. So, suppose you have a slot here, you have a slot there, you have a slot there, you have a slot there for say R phase, and these are the coils. Suppose I have wound the machine for 4 poles. So, this is cross, you pass some current, its return is here dot, it is cross and it is dot, and you get 4 poles created. This will be north, this will be south, this will be north, and this will be south, because lines of forces etc. will be there, it will come out. Now, I will change the connection of this coils such that the current distribution pattern I can change it like this. This is the slots are there, windings are there. Can I use these same conductors to have 2 poles? Yes, you can have. Only thing you make sure that when it carries cross, this also carries cross, and these 2 carries dot and dot. Then it will give you only 2 poles. This half 1/4, I mean this half will be north pole, that half will be south pole. So, it is possible. We will not go much into this simply because earlier days these were very nice methods which were proposed by after doing lot of research work that is you have as one 3 phase winding, but some terminal should be available to the users. So, by interconnecting those group phases etc., you can generate 2 poles in the ratio of 1:2 like that. But obviously, once again so many terminals you have to bring out from the machines, not simply 2 terminals for R phase, 2 terminals for Y phase or 2 terminals for B phase. To carry out this kind of operation, you require many terminals to be brought out, maybe from the groups of a particular phase. So, it was cumbersome that way, and you have to change that interconnection only to get 2 level of speeds, that is all, and having of course, a cage rotor. But with passage of time, those methods are nowadays no longer used, simply because we will at least highlight those points, because with the advent of fast switching with solid state switches, you can make good inverter and you can vary the frequency of the supply to control the synchronous speed of the induction motor, hence its speed, which is much more elegant and easier to do than to ask for 2 separate stator coils or 1 3 phase stator coils with some extra terminals brought out, which had to be always reconnected in a particular fashion to give you different level of speeds. Because ultimately, as I told you, this is true, synchronous speed is equal to 120 f by p. So, earlier it looked like supply frequency you cannot control, because it is the bus voltage that is only we are getting. So, people thought with the same windings whether p can be changed, hence ns, and this cannot be done continuously, no continuous speed control is possible, only 2 discrete level of speed you can have from one of the induction, from the same induction motor. Anyway, we will continue our discussion from this point. Thank you.